On the left, there's a cartoon of a neural network, just to give you an idea of what's going on. The data comes in at the top and visits each of the boxes, and the data flows along the arrows to the different boxes. The boxes are typically convolutions or deconvolutions with ReLUs. The green boxes are pooling layers. And the important thing about this is that the data produced by one box is then consumed by the next box, and then you don't need it anymore. You can throw it away. So all of that temporary data that gets created and destroyed as you flow through the network, there's no need to store that off-chip in DRAM. So we keep all that data in SRAM, and I'll explain why that's super important in a few minutes. If you look over on the right side of this, you can see that in this network, of the 35 billion operations, almost all of them are convolution, which is based on dot products. The rest are deconvolution, also based on dot product. And then ReLU and pooling, which are relatively simple operations. So if you were designing some hardware, you'd clearly target doing dot products, which are based on multiply add, and really kill that. But imagine that you sped it up by a factor of 10,000. So 100% all of a sudden turns into 0.1%, 0.01%. And suddenly the ReLU and pooling operations are going to be quite significant. So our hardware design includes dedicated resources for processing ReLU and pooling as well. Now, this chip is operating in a thermally constrained environment. So we had to be very careful about how we burn that power. We want to maximize the amount of arithmetic we can do. So we picked integer add. It's 9 times less energy than the corresponding floating point add. And we picked 8-bit by 8-bit integer multiply, which is significantly less power than other multiply operations and is probably enough accuracy to get good results. In terms of memory, we chose to use SRAM as much as possible, and you can see there that going off-chip to DRAM is approximately 100 times more expensive in terms of energy consumption than using local SRAM. So clearly, we want to use local SRAM as much as possible. In terms of control, this is data that was published in a paper by Mark Horowitz at ISSCC, where he sort of critiqued how much power it takes to execute a single instruction on a regular integer CPU. And you can see that the add operation is only 0.15% of the total power. All the rest of the power is control overhead and bookkeeping. So in our design, we sought to basically get rid of all that as much as possible, because what we're really interested in is arithmetic.